In this video, I'm going to talk about theoretical yield and actual yield. Theoretical yield is what we get whenever we use stoichiometry in order to figure out an amount of product that would be produced. So anytime that we work through stoichiometric coefficients from a starting material, we're usually talking about theoretical yield. Essentially, theoretical yield is the max of a product we can make. So when you go through limiting reagent problems, you end up essentially calculating out the theoretical yield. We can get this is a ratio in between. Actual yield is the amount that you really make. It's very, very rare in chemistry in order to get a 100% yield. In fact, a lot of industrial type reactions that occur do not have a very high percent yield. Many times, jobs can be gained just by simply attempting to come up with a new way to do something in order to get a better yield. So the actual yield is always going to be less than the theoretical yield, except for in some rare cases, which I'll talk about in a minute. The percent yield is a ratio in between actual yield and theoretical yield. This also makes it similar to our percent masses, our percent abundance, everything that we've done in percents. This means that it also can be used as a dimensional analysis ratio. For example, if I say you have 69% yield, we could write this as 69 whatever grams usually of actual per 100 grams theoretical. We usually get lower than 100% yield. So very often this will happen due to equilibrium. In other words, a reaction goes all the way forward until it can't go forward anymore, and then it goes back a little bit. Difficult or multiple reactions where things just aren't carried through. Underneath difficult reactions, we can kind of think of these as reactions that require a lot of energy, or reactions that require very specific connections in order to occur. Because remember, a reaction is essentially a collision between different species. Now, these are okay reasons. These are okay. We know they happen and it's fine. This is why we give you a little bit of a buffer room whenever we're calculating unknowns in lab. There are other reasons why you can get less than 100% yield. And I'm going to draw a line. Loss of product. In other words, you spill stuff. Incorrect values. You didn't write down the correct masses. Loss of reactants. Again, you spill stuff. These are not okay. This means you screwed up. Okay? Additionally, if you end up getting greater than 100% yield, this usually means you have some type of contamination, or you didn't do the measurements correctly. We can never make more than what we started with. That's the law of conservation of mass. So next, let's take a look at an example of using percent yield. So with this problem, we have some very strange organic names. We have azobenzene, and what I recommend you do whenever you come across something like this, because a lot of times I'll pull organic chemistry into here because you're going to see it someday, highlight it. There's azobenzene. Okay, it can be prepared from nitrobenzene, so I'm going to label that as something different. Nitrobenzene. Nitrobenzene. By reaction with triethylene glycol, we got another weird one, so I'll make this one green and green. In the presence of zinc and potassium hydroxide, these are catalysts. In one reaction, 0.30 liters of nitrobenzene. Okay, what color do we use for nitrobenzene? So I'm going to go like this. Notice that this is one of those times whenever I used rho, right, the Greek-looking P for density, and triethylene glycol, so we'll label this one green with its density, and it yields 55 grams of azobenzene. So this would be my actual yield. I need to determine the percent yield. So that means I'm going to have to find my theoretical yield. Well, I was given two different amounts, which means this is a limiting reagent problem. Now in Chem 4, a lot of times you just do the limiting reagent problem and that's it. Not so much anymore. Limiting reagent problems are oftentimes a first step, so you have to be able to readily identify these guys. If you have two or more substances in a reaction, you got to do a limiting reagent problem. So I'm going to call this NB, nitrobenzene, and I'm going to call this TG for triethylene glycol. So I have 0.30 liters of nitrobenzene. I'm going to start my dimensional analysis now. I'm going to run them both through, just like with any other limiting reagent problem. First, I'm going to go from liters to milliliters because that's what my density is in. And then for every 1 milliliter, I have 1.20 grams of nitrobenzene. I need the molar mass of nitrobenzene, which is 123.111 grams in 1 mole nitrobenzene. Now that I'm in moles, I can use Common Core and go from 2 moles nitrobenzene, and I'll call this azo just for brevity. So I have 1 mole azobenzene, and then I need to go into grams. So for every 1 mole azobenzene, I have 182.2248 grams. Multiply across the top, divide by the bottom. I have 266, 6 being my last sig fig, grams azobenzene. But that's not the end, right? This is just if my nitrobenzene is the limiting reagent. Now we got to test through with triethylene glycol. So I have a whole new dimensional analysis grid. So again, we're going to go from 1 liter to 1,000 mils. Back into milliliters to use the density. And molar mass to go into moles. Using the complete balance equation, I have 4 moles to 1 mole. And then for every 1 mole, I have 182.2248 grams. Multiply across the top, divide by the bottom, and this gives me 101 grams azobenzene, 0 being my last sig fig. So out of these two, who produces the least? This one. This is my limiting reagent. That means that this is my theoretical yield. To find my percent yield, I take my 55 grams divided by my 101 grams. So this is actual divided by theoretical times 100, and I end up getting 54%. Again, remember that these percents can be used as ratios. So for example, if I wanted to run through and say, okay, the next reaction that I did, I ended up having the same percent yield, how many grams would I make if I react X and Y? Well, I could rewrite this as 54 grams actual to 100 grams theoretical.